Welcome to Mathmania Academy. In this video, we are going to discuss the linear algebra questions which were asked in June 2018. Here, the first question is A is given to be a matrix of order m by n and B is given to be a matrix of order n by m with the condition that m is smaller than n. Okay. And in the options, they are asking about whether the matrix AB is singular or non-singular or BA is singular or non-singular. Okay. But we are not given that what is the exact matrix A or B. Okay, fine. If the order of A and B are known, then we can very well find out the order of the matrices AB and BA. AB will be of order m by m and B is of order n by n. Sorry, I meant to say that BA is of order n by n. So in this case, what can we say? Now we'll have to check the singularity or non-singularity. If we have to check the singularity or non-singularity, we'll have to examine determinant of AB, whether it is equal to 0 or not equal to 0. Okay, the same goes here as well. Determinant of BA is 0 or not equal to 0. We'll have to examine this. Okay, how do we calculate the determinant if we are not aware of what the exact matrices are? So in that case, we must be aware of the results that we know. That is, determinant of a matrix is the product of the eigenvalues. Okay, suppose A is a matrix of, okay, let me have it as M, where M is an n by n matrix. If it is so, we can write down the determinant in this way. Okay, if we have to get the determinant of some matrix is 0, then what happens? Then what should happen? If one of the eigenvalue is 0, then clearly the determinant is 0, hence the matrix is singular. Okay, so that is what we are going to examine. Even now, in order to find the eigenvalues, we don't know what the matrices are. Okay, we have two matrices here, A and B, with which we have found two products AB and BA. The relation between AB and BA tells us what? Characteristic polynomial of AB can be equated to the characteristic polynomial of BA just by multiplying the corresponding some x power terms, right? This is of order m by m, so we'll have to multiply n here and here m. Okay, now you can take either x power n or x power m to the other side. That you have to decide based on the value of m and n. Here m is given to be the smaller value, so what you can do is that you can take this one so that it remains this x power n minus m has a positive power, okay, into characteristic polynomial of AB of x, in that is same as that of characteristic polynomial of BA, right? So it means what? CBA of x has 0 as an eigenvalue. How do we conclude it? No matter what is the characteristic polynomial of AB, but that polynomial has to be multiplied with x power n minus m. That n minus m is a positive quantity, hence 0 must be an eigenvalue of the matrix BA. When okay, actually this BA has 0 as an eigenvalue, right? When BA has 0 as an eigenvalue, that is always singular. No matter what B and A you choose, your matrix BA is always singular. That have no possibility of becoming a non-singular matrix, right? Moving to the next question. Here A is given to be a 2 by 2 matrix over R and determinant of this stuff is given, and we'll have to conclude from this. Okay, let A be any 2 by 2 matrix over R. Okay, then what is determinant of A? That is AD minus BC. Fine. Okay, what is A plus identity? The matrix, it is A plus 1, B, C, D plus 1. and determinant of A plus identity is A plus 1 product with D plus 1 minus BC, and this is simply AD plus A plus D plus 1 minus BC. Okay. Now, given that determinant of A plus I is same as that of 1 plus determinant of A, right? So this quantity is AD plus A plus D plus 1 minus BC, which is same as that of 1 plus AD minus BC. So the terms gets cancelled and we are left with A plus D equals 0. What is this A plus D? That is the trace of a given matrix. So trace of A has to be equal to 0. That's it. Right? Actually, if you see the previous example and this example, we have just proved it. We were looking for the answers. We were not trying to discard the options, because here if you have to choose suitable matrices such that you will have to discard 3 options, that will involve some time. That is why we have proceeded with the theoretical ideology. Okay, it hardly took, since I am explaining it to you guys, it hardly took nearly 2 to 3 minutes. But when you have that idea, you can very well just do it in 30 seconds, 30 to 45 seconds maximum, right? So few questions, just by looking at few questions, our mind should get some idea. It is a 2 by 2 matrix. Instead of picking a random 2 by 2 matrix and working out everything, and if you are about to choose a matrix satisfying this condition, this is quite difficult. That is why we have done it theoretically. Okay, moving to the next question. Here a system of equations is given and we are asked to check whether it will have a solution in real numbers, rational numbers, complex numbers, or it will not have a solution at all. So these things are to be examined. Here in the equations it is given x, x square, xy, y. You may be thinking there are only 2 variables x and y, and with which they have manipulated something. Actually, you don't have to think that way. Just put it in a matrix form, that 1 2 3 0 2 1 3 1 1 minus 1 0 1 multiplied with what? X, x square, xy, y. Just treat them as separate variables. Okay, instead of naming the variables x, y, z and w, they have named it this way. Just think that way and proceed. Okay, now in order for the system to have a unique solution, what must we have? We must have rank of AB is same as that of rank of A, right? Okay, let us first of all examine the rank. Okay, what is the augmented matrix here? So it is 1 2 3 0 6 2 1 3 1 5 1 minus 1 0 1 7. Okay, if you perform the linear elementary transformations, you would end up in a matrix. I am going to give you the final matrix. Just R2, you have to do R2 minus 2R1, then R3 is simply R3 minus R1, after which what you have to do is that you just have to do R3 minus R2. Okay, after performing these elementary transformations, what you are going to have is, so here your rank of AB is 3, but rank of A is 2. In this case, the system will not have any solution. That is, the system has no solution, right? Moving to the next question, we are asked to find out the trace of a matrix. Okay, part 20, let that be. A is what? 210, 020, 003, and they are asking for trace of a power 20. Okay, since A is a upper triangular matrix, what do you get? 2, 2, 3 are eigenvalues, right? If this is so, 2 power 20, 2 power 20, 3 power 20 are eigenvalues of A power 20. Therefore, trace of A power 20 is what? Sum of eigenvalues. That is 2 power 20 plus 2 power 20 plus 3 power 20. This is 2 times of 2 power 20 plus 3 power 20. That's it. Moving to the next question. Here it is given that Rn n may be any value which is bigger than or equals to and is equipped with a standard inner product. Standard inner product means if you take a vector in Rn, okay, if you take two vectors in Rn, standard inner product means the usual dot product that we perform in vector calculus, right? And we have n vectors forming an orthonormal basis. By orthonormal basis, what do they mean? They mean inner product of vi comma vj is 0 for every I not equals j, and norm of vi is 1. This is what they mean by orthonormal basis. Now we'll have to check A is a matrix which is formed by the column vectors v1 through vn. Okay, then what should we check? Okay, for which we'll have to make use of just a result that A is an orthogonal matrix if and only if columns of the matrix are orthonormal. What do we mean by okay? Here orthonormal means A transpose is equal to A transpose A equals identity. So from which A inverse, if you multiply A inverse throughout, what do you get? A inverse. So it is simply A transpose is A inverse. Option 3. Fine. So whenever Rn orthonormal basis, if these informations are given to you, you may think that orthonormal bases are Ej. It is what 0 0, jth entry is 1 and the rest 0. So you may think this way. Yes, I am agreeing to the fact that this collection where j running, okay, this collection with j running from 1 to n is an orthonormal basis, but it is not necessary that you will have to consider it in E1 E2 this order only. You may also consider, if you consider it in this order E1 E2 till En, then the matrix that you form out of these would be the identity matrix. In this case, your A is same as that of A inverse, your A is same as that of A transpose, and the determinant of A is 1 and A inverse is A transpose. All these are satisfied. But when you just interchange any of these things, okay, for simplicity purpose, for n is equal to 3, let me explain you. What I am saying is that instead of having an identity matrix, just interchange first two columns 0 1 0 1 0 0 0 0 1. Here, if you evaluate the determinant which is not equal to 1, that is going to be minus 1, I suppose, right? And when you take the transpose, okay, you are getting the same, I suppose, right? And your A is same as that of A inverse, that we'll have to examine and check. Okay, let us go for the higher case. Okay, 0 1 0 0 0 0 0 1 1 0 0 0 0 0 1 0. This is one such matrix. You can very well check this is an orthogonal matrix. Just find its transpose and multiply, you will get an identity. Okay, you can very well check this is an orthogonal matrix, but other three options may not hold here. This is what I am trying to say. Whenever, just by looking at the orthonormal basis, if your mind goes to the standard vectors, that is these collections ENs, and when you arrange it in the same order in which it is defined, that would end up in an identity matrix. For identity matrix, all the four options are true. Okay, with the help of the options, you here we are talking something in general. When you are talking something in general, with examples you can discard options, but you cannot accept options when something is spoken in general. Okay, we have completed part B questions. Now let us move to the part C questions. Here it is given that V is a vector space over C of dimension n, and T is a linear transformation with only one as eigenvalue. Then which of the following must be true? Okay, here also it is matrix of T with respect to some basis has 1 as an eigenvalue. For simplicity purpose, let us consider it has 1 in the diagonal elements, and below diagonal let us take everything as 0. For simplicity purpose, I am considering this one. Okay, what is the above diagonal? That can be anything. Okay, if you consider in the above diagonal also you have 0, this is nothing but the identity matrix. For identity matrix, all the four options will be true. We are unable to discard anything, right? Okay, let this be a n by n matrix. Now let me have only 1 here and the rest entry 0. That is, I am assuming, actually here they have given that with this information only 1 as an eigenvalue. What is the characteristic polynomial of this T? That is x minus 1 to the power n. Okay, so by Cayley-Hamilton theorem, what do we get? The characteristic polynomial will satisfy the given matrix. Therefore, T minus identity whole power n is 0. If it is true, then n whole square is also true. That is, T minus identity whole power 2n is 0. So we get option 3 and 4 are true in general. Okay, just by the given information we have proved it. Okay, now we will have to examine whether option 1 and 2 are not true or not. If this is the characteristic polynomial, then the minimal polynomial has the chance either it is x minus 1 or x minus 1 square, x minus 1 cube till x minus 1 to the power n. If this is the minimal polynomial, then you will have the chance that your T is the identity matrix. In that case only your first option is true. But there is no guarantee that this is your minimal polynomial. What if this is our minimal polynomial? In this case what happens? T minus I whole square is 0. Okay, but there is no guarantee that your x minus 1 square is also a minimal polynomial. So your minimal polynomial has these many chances. N different chances are there for the minimal polynomial. So in this case we cannot we cannot conclude anything. Okay, let me write this way. Suppose the minimal polynomial takes any of these chances. In this case also, your x minus 1 whole power n would be 0. Even though your minimal polynomial takes these many chances, these n minus 1 chances, this is true in general. But suppose your minimal polynomial takes this chance, then what happens? None of these is true. Okay, so your T minus I whole power n minus 1 equals 0, that need not be true in general, for which you can take a matrix. I am giving you a matrix, have 1 in the diagonal entries, Okay, the remaining 0, and try to have non-zero entries here. Okay, with this t, try, you can have all the entries over here are non-zero. Okay, just try with this. You can pick an matrix of any arbitrary order. You just give a try. This would give you that t minus I whole power n is 0, but okay, t minus n is t minus I to the power k is 0 for k bigger than or equals n, and is not equal to 0 for k smaller than n. This is going to happen, right? Okay, now let's move to the next question. In this question, it is said that A is a 5 by 5 matrix and the dimension of the solution space AX is 0 is at least 2. Okay, what is it? Dimension of the solution. As of now, we are looking for the dimension of the collection of X in R5 such that AX is 0. Dimension of this set is at least 2. This is what they have given, right? Actually, what is this? How did I come to a conclusion that we are taking it in R5? Because A is given to be a matrix of order 5 by 5. Therefore, A can be treated as a mapping from R5 to R5. Okay, so this is gonna happen. What is it? It is the dimension of the null space of A, which is given to be bigger than or equals to. This means nullity of A is bigger than or equals to. Now, by rank nullity theorem, what do we have? Rank of A plus nullity of A is 5. Okay, what is rank of A? It is 5 minus nullity of A. We have nullity of A is bigger than or equals to, therefore minus nullity of A is smaller than or equals minus 2. Therefore, rank of A is 5 minus 2. Okay, smaller than or equals 5 minus 2, which is 3. Rank of A is smaller than or equals 3. But in the options, they are asking for rank of A squared. Okay, let us check it. Okay, we have a result that let me write it in different color. Rank of AB is rank of A minus dimension of kernel of A intersection range of B. Okay, here what is happening? Our A and B are same, right? So rank of A square, that is rank of A minus dimension of kernel of A intersection range of A. And when the linear transformation is defined from a finite dimensional vector space to a finite dimensional vector space, in that case kernel and range will have only 0 in the intersection. Therefore, this is the case. Rank of A square minus dimension of set 0, which is nothing but simply rank of A minus 0, which is smaller than or equals 3. Therefore, rank of A square is smaller than or equals 3. Note that rank of A square is smaller than or equals 3, which is strictly smaller than 5. Okay, in that case 0, there are only at most 3 linearly independent rows in A square. This forces determinant of A square is 0. Okay, A square will have 5 columns or 5 rows. Okay, out of which maximum of 3 can be linearly independent, which means there are minimum 2 linearly dependent rows or columns, hence the determinant is 0. Right, moving to the next question. Here it is given that A is any matrix in M3 of R such that A power 8 is identity. Okay, if that is so, you can consider the polynomial p of x as x power 8 minus 1 equals 0. So the minimal polynomial of the matrix A will divide this polynomial. This one, how can you write this p of x as, it is x power 8 minus 1. That one, let me write it as x power 4 plus 1 product with x power 4 minus 1. Again, this can be split as x power 4 plus 1. This is there as it is, x square plus 1 into x square minus 1. Again, you can split it in the way that x power 4 plus 1, x square plus 1, x plus 1 into x minus 1. So these are the possibilities, right? All are distinct in nature. Okay, so this is one. Why did we come with which, what are we going to do? If you look for the minimal polynomial of this matrix must involve distinct things. Okay, so it is saying that this is going to give you a different thing, this is different thing, all these terms are distinct, no term is repeated, therefore your minimal polynomial has to be same as that of this p of x. Okay, therefore it is for option 1 and 2 claims that the minimal polynomial can only be of degree 2 or 3. No, nothing. So even if we stop it in this stage, it has 2. We have factors, we are dealing in R, so even these things can be factored. If I have to factor this thing, then I should have x plus iota product with x minus iota, but that iota is not a member of R, that is why that cannot be factored further. In R we have come to the maximum factorization, from which it is clear that the degree of minimal polynomial is bigger than 4, therefore it cannot be of degree 2 or 3. That is why option 2 and 3 are false. Okay, so option 3 claims that the matrix A has to be either the identity or minus identity. It is not so, we have seen. Okay, with this ideology itself, it is clear. Okay, now sorry, minimal polynomial cannot be actually this cannot be p of x, since matrix is of order 3. This polynomial is annihilating this, and hence with which you cannot conclude anything. That is what I am coming to say. If you have this and this, if you have this option, this tells that your A has to be identity. Suppose if you have this option, this tells that A has to be minus identity. But if you have this x squared plus 1 with any of these two terms, then what? Then also that can be a minimal polynomial. So you cannot come to any conclusion of that sort. Okay, minimal polynomial cannot be of degree 8 since matrix is of order 3. Okay, and let us come to the last option. So there are uncountably many A satisfying the above. Is it so? Let me try to construct a matrix A that gives me A power 8 as identity. So I don't have to go till A power 8. If my A square is identity, then also it tells that A power 8 is also identity. Let me try this one. Okay, so basically what I have is my identity matrix, right? Okay, but this will end up in what? My third category. Okay, so what I am doing is that I am just interchanging the columns. Now let me evaluate A square. So what I get, 1 here and rest zeros, and this is 0 1 0, and when I do here I am getting this one. Okay, so basically this matrix I am able to find out one such matrix which is not listed in option 3. Okay, but option 4 is asking for uncountably many A satisfying this condition. Okay, what I am doing is that here, if you observe this entry, when I multiplied this entry with this, that contributed this one. Okay, that contributed my first entry. And similarly, when I product this row with this column, okay, first what happened, this row with this column gave me this one, okay, then this row with this column gave me this entry. Okay, in both the cases we had only these ones, that value 1 performed it. Okay, let me put any non-zero entry here. Let me make it as alpha. If I simply make it as alpha, then what would I have? I would have alpha and alpha in these places, but I need 1 there. So what am I going to do is that I am going to change this 1 as 1 upon alpha. I am choosing this alpha to be a non-zero real number. So here what is going to happen? This alpha with 1 upon alpha would give me 1 only. This 1 upon alpha with this alpha is going to give 1 only. So my A square is getting an identity matrix. Therefore, my A power 8 is also an identity matrix. So I am able to, as of now, I am able to produce uncountably many A satisfying the condition A square equals identity. Therefore, it will satisfy A power 8 is also an identity matrix. So even for this degree 2, I am able to produce uncountably many. When I go for much more powers, of course it is going to happen, right? Hence option 4 is true. And anyway, we have discarded options 1, 2 and 3. Hence option 4 has to be right, but we proved it too. The next question says that A is an n by n matrix with n bigger than 1 which satisfies some condition. Okay, and I and 0 denotes the identity matrix of order n by n, and 0 matrix of order n. Okay, then which of the following are true? Okay, if the matrix A is a square matrix of order n with n bigger than 1, so n takes the minimum of n bigger than or equals 2. Okay, so here what is it? We have a polynomial, right, which is x square minus 7x plus 12, and the given matrix A is annihilated by this polynomial. Okay, if this is so, and this can be factored into x minus 3 into x minus 4, this you can very well do it. Okay, therefore the minimal polynomial of this matrix should divide this polynomial, which is simply x minus 3 times of x minus 4. Since it involves only the linear factors, the minimal polynomial itself is this polynomial, that is x minus 3 times of x minus 4. But you don't know what is the order of the matrix. If you have to find out the characteristic polynomial of this matrix, then it is x minus 3 times of some k product with x minus 4 times of n minus k. So since the minimal polynomial has only these two factors can take place in the characteristic polynomial. So it is very evident that 3 and 4 are the eigenvalues, but the multiplicity is unknown as of now. Okay, only 3 and 4 are going to be the eigenvalues. Hence, the determinant of the matrix cannot be equal to 0, since it is going to be a product of 3's and 4's. Therefore, this tells us that the determinant is not 0. Hence, the matrix is invertible. Okay. And how did we get this 3 and 4? Just by solving this one, right? Therefore, the eigenvalues will also satisfy this one. Hence, option 4 is also true, right? Okay. Or if you just expand this one, this is what you are going to have. Okay. 3 and 4 are the eigenvalues. When you substitute 3 into it and 4 into it, it will satisfy this equation. Instead of x, they have lambda in the question. That's it, right? And option 213 claims that trace will satisfy minimal polynomial, determinant will satisfy minimal polynomial. That need not be true, right? If you have to prove these two things are true, then you may pick an example. For simplicity purpose, let me choose my A to be a diagonal matrix of order 2 with 3 and 4 in the diagonal. Okay, here my trace is what? Trace of A is 7 and the determinant of A is 12. Okay, what is 7 square minus 7 times of 7 plus 12 times of 2? So it is 49 minus 49 plus 24, which is not equal to 0. Therefore option 2 is wrong. And determinant is 12 square minus 7 times of 12 plus 12. It is 144 minus 84 plus 12, which is again not 0. So option 3 is also false. Okay, if you don't find any enough evidence to prove something is wrong, just try to produce an example that proves that option is generally wrong. Okay, they have given that n is bigger than 1, and if you find the characteristic polynomial, that is going to be something in option 4. Okay, we have evaluated the trace and determinant and verified option 2 and 3 are wrong. Moving to the next question. Here A is given to be a matrix over R with characteristic polynomial. Something is given that involves two factors, x minus 3 and x minus 2, and x minus 3 is appearing twice and x minus 2 is appearing 4 times, and the minimal polynomial is given to be of something like this. So since in minimal polynomial x minus 3 is appearing only once, in Jordan block there is a 1 by 1 block for x equals 3, and there is a 2 by 2 block for x equals 2. But in characteristic polynomial, this x minus 3 is appearing twice, and there should be at least one by 1 block for x equals 3. Therefore the 3 will appear separately in the diagonal positions. Okay, coming to this x minus 2, there should be a 2 by 2 block for this 2, so this block has to be there at least once. Okay, and in characteristic polynomial x minus 2 whole power 4 is there. So when you make block for this 2, this should be there once. This 2 by 2 block can be formed using the same or two separate blocks. These two are the possibilities for x minus 2 thing, right? And for 3 by 3 there can be only this is the possibility. So with which we can check our options. The first option claims that we have this 2 by 2 block for 3. Okay, fine, and this is fine, this is fine, but this one should not be there. This should be filled with 0. Therefore option 1 is wrong. Okay, coming to the option 2, this is fine. Okay, and this is fine, and this thing is there. Yeah, fine. Okay, so here actually the remaining entries are filled with 0. Okay, you don't have to look at it as a separate 2 by 2 blocks, just look at it as a entire 4 by 4 block. So this option is not here. Only these two are the possibilities for this eigenvalue 2, and here it took the second option. Okay, moving to the third option. Yeah, it took the first option. Yes, 2 and 3 are right. Okay, now coming to the fourth option. Here for 3 we cannot have a 2 by 2 block, that is why it is wrong. That's it. Moving to the next question. V is given to be an inner product space and S be a subset. Remember, this S is a subset. S not necessary a subspace. And S bar denotes the closure of S in V with respect to the topology induced by a metric given by the inner product. Okay, so we must think it in these ways. Like, we should have an inner product. With that inner product, we must be able to define a norm, and with that norm, we must induce a topology. These things are there, right? With which we'll have to check which of the following are true. Okay, in this case, instead of proving it theoretically, I would like to solve it by choosing the particular examples. By discarding the options, I am going to prove this. Okay, let me choose V to be R3. Okay, and the inner product is, if I choose XY, the inner product defined as x1 y1 plus x2 y2 plus x3 y3, the usual inner product. Okay, if I define the norm of x means what? It would be under root x1 square, x2 square and x3 square. If I have to induce a topology with this norm, if I have to define a metric, that is d of xy, that would be under root x1 minus y1 square plus x2 minus y2 square, x3 minus y3 square. Okay, so with this metric we'll have to induce a topology, and there we are going to talk these things. That is, just looking at it as a problem in real analysis, we have taken a Euclidean space R3 with the standard Euclidean metric. Okay, now let me choose the set S to be the collection of points. Okay, let me fix it to be 0 such that x square plus y square is smaller than 1. Or I can, okay, this is enough. Okay, this is my S. Okay, what is it? If you just see, let this be x, let this be y, and let this be z. Okay, here what did we take? X square plus y square is smaller than 1. That means in the xy plane we have chosen a circle without the boundary, right? And or we can choose what? Yeah, this is fine. What would be S bar? S bar is S union its limit points as well. Okay, here S bar denote its closure means we'll have to include the limit points as well, right? I hope it is the same collection with x square plus y square less than or equals 1. If I am not wrong, I am not very yeah, I guess if it is set, then this is fine. The 0 is there. So here the neighborhoods will be of sphere form. We are able to, yes, actually the closure will have something more than this too. This is not exactly the closure. The closure contains this. That's it. Okay, now if we look for the orthogonal complement of S, it is the collection of points A, B, C in R3 such that inner product of, what is the inner product? That is okay, inner product of this ABC with the entries that we choose from that thing is 0. that is the collection of ABC in R3 such that this would be what? XA plus BY is 0. Okay, so this is going to be the orthogonal complement of S. And if we have to identify the basis for which, what can it be? This has to be equal to 0. So if you find the basis, this can have the basis 1 0 0 and 0 1 0, and if you identify, this would turn to be 0 0 C in R3, because if it has to be 0, it will force your A and B should be 0, right? Because you don't always take X and Y are equal. In that case, if you choose X and Y are equal, then your A can be equal to minus B, but it is not always the case. For all X and Y, if it has to be 0 means it will force your A and B to be 0. So in that case, you must have only C in it. So this is the orthogonal complement. And what is the orthogonal complement of the orthogonal complement of S? If you proceed this way, you would get simply xy0 in R3, the entire thing. Okay, which means this is simply the your whole xy plane, and this is your z-axis. Okay, that is your entire z-axis, and this is your xy plane. These things from the geometrical point of view you are able to understand. That is why I am giving these things. Okay, this x square, I have fixed this 0, so I am getting a circle of radius 1 in xy plane. If I had z here, then what happens is that I would have a cone. Okay, fine. So if you see, your S complement, whole complement is your entire xy plane, and your S closure is what? It is some set consisting of this set, this one. Okay, this closed circle or closed disk, actually not circle, closed disk. It is not a circle, it is a disk of radius 1, open disk of radius 1. Okay, and it will contain some points from in the space. Okay, so these two are not same, and this S is not same as that of the complement of the complement. So option 1 and 2 are not true. Okay, what is span of S? First of all, we'll have to find it, right? So span of S means the linear combination of points in that S. Okay, if you choose any 2 points, any different points from this circle, and you will have to form a linear combination. If you choose any points from the circle, that is lying on the xy plane only, right? If you find the linear combination also, that is going to lie in the xy plane. You may ask me a question. We are choosing points in the open disk. Suppose I am choosing a point somewhere. Okay, let me choose a point somewhere here and here. Be that point be however small, I am able to identify one such point when I multiply that with that quantity. If I am choosing some point here near 0, let that be 0 0.5 comma 0 0.1 comma 0, this is lying inside it. When I multiply a quantity which is 10 power these kind of things, that will become larger quantity. So however small the value that I have inside, I am able to multiply some larger quantity as a scalar to neutralize it. Okay, so what I am going to have is that I would have the span of S would be the xy plane itself. Okay, when you take the closure, yes, exactly, it is xy plane. Just look at it in the geometric point of view. Okay, whatever they have specified here, that we have converted to geometric point of view. That is why That is why we can easily work with this. Okay, in circle, the disk, in the disk you can arbitrarily pick any 2 points. Okay, the scalar, if I am choosing x1 y1 0 plus x2 y2 0, this alpha and beta you can choose accordingly, so that this is some general point in xy plane. So the closure is also a xy plane. So the choice of this alpha and beta, these two things you will have to choose from the real numbers. So you are free to choose whatever real number you like. So this proves that this is true. Okay, actually we don't find any evidence to prove that is false. Fine. If this is a subset, and we have a result in linear algebra that S be any subset, the span of S is a subspace. Okay, this is a subspace which is smallest containing the set S. Okay, so you will first of all, the span of S means span of S. Coming to our problem, what is the span of S? We will have to identify the smallest subspace that consists of this disk. So in that case, we would end up with what? XY plane only. So the closure is also XY plane, right? With that idea only, we have come to this, right? And here also you just identify what is S complement, whole complement to the complement. S complement is XY plane. So what is orthogonal to it? It is Z axis. So it is trivial from this example, or if you have to prove it generally, yes, you can very well prove it. Okay, let me do here. S complement means it is the collection of vectors in V such that inner product of x comma y is 0 for all x in S, right? S complement, whole complement means again collection of z in V such that y comma inner product y comma z is 0 for all y in S complement. Okay, and what is S complement, whole complement? It is the collection of points in V such that inner product x comma y is 0 for all x in S complement, the whole complement. So whatever may be the point that you choose from this set, if you choose something in this set S complement, whole complement, that is orthogonal to this S complement. That is what it is saying. So we would go back just by definitions. You just write down the definition from which also you can very well prove this option. Okay, moving to the last question of this video. A matrix A is given and a quadratic form is specified. First of all, let us write down what is the quadratic form of this thing. So this would give us x square plus 2xy minus 2yz plus z square. Okay, we are asked to check which of the following are true. The matrix of second order partial derivatives of the quadratic form, which means if you the matrix that they are talking is del square q upon del x2, del square q upon del x del y, del square q upon del x del z, and del square q upon del y del x, del square q upon del y square, del square q upon del y del z, del square q upon del z del x, del square q upon del z del y, and del square q upon del z square. Okay, Just identify this matrix. Okay, these two are same. Am I right? Since this is a continuous one, these two are same. So whatever you find for one thing, that has to be equally distributed to these two places. That is A12 position and A21 position should share it. Okay, so when you differentiate twice, you are going to get, when you differentiate twice with respect to x, you would get 2, and when you differentiate with respect to x and then y, you would get 2. So this has to be spread over these two things, and similarly this position will be shared like this, and this is twice. The rest entries are 0. There option 1 claims that this matrix is twice A. No, it is not. So option 1 is false. The rank of the quadratic form is 2. Rank of the quadratic form is same as that of the rank of the matrix associated with it. It has only 2 independent rows. So therefore the rank is 2. Okay. Since it is an upper triangular matrix, the eigenvalues are what? Eigenvalues of the matrix A are 1, 0 and 1. Therefore the signature 1, 0 and 1. Therefore the signature is, it has 2 positive eigenvalues and 1, 0. Therefore the signature is plus plus 0. That is also true. The quadratic form takes the value 0 for some non-zero vector x, y, z. Okay, they are claiming. Okay, if it is so, it should take 0 as, okay, since 0 is an eigenvector, just a minute. Option 4 claims what? The quadratic form Q takes the value 0 for some non-zero vector. That is, it is claiming that x square plus 2xy minus 2yz plus z square should be equal to 0 for some non-zero xyz in R3. This is what it claims. Is it possible? Let us check, because 0 is one of the eigenvalue. So 0 is one of the eigenvalue. There exists a non-zero vector in R3 such that AU is 0U, which is 0, right? You just multiply its transpose with it, that is 0 only. Yeah, we are therefore the quadratic form of this U is 0, which is a non-zero one. Since 0 is an eigenvalue, we are able to identify the eigenvector corresponding to that 0, with which we are able to produce it. Yes, option 4 is also true. That's it about this here. Thank you.